professor at IIT Palakkad. We also have Professor Sundararajan, who is also from IIT Palakkad, and he will be talking on hydrogen production technologies later in the afternoon. I understand that many of you, the students and also faculty here, are mainly from electrical engineering, or your background is electrical engineering. Is that right? Right. So there are some mechanical engineering faculty also, that's good. So I'll try to make it as generic as possible, and also walk you through the various aspects of hydrogen energy technologies, the whole life cycle of hydrogen, why it is important to talk about hydrogen energy, and give you some perspective on this. Okay. You can stop me whenever you have any questions, or we could hold the questions to the end also, as you want to do. So the topic is Introduction to Hydrogen Energy and its various applications. Hydrogen energy is essentially energy from hydrogen as the source from which you draw it. Okay. And what are the applications? The most common application is, of course, hydrogen being used in a fuel cell, which is already there in your FDP title itself, to generate electricity directly, or it could be to generate heat, or in various other applications which we will see. So hydrogen energy has applications in various areas, but it's also important to understand what the impact of hydrogen is. Okay, see, why do we have to go for hydrogen as an alternative, or why should we choose hydrogen over any other conventional fuel source? So this is something that we have to understand. So the question is, or rather the aspect that we have to think about is whether hydrogen is the elixir. Hydrogen, as we all know, is available naturally in the Earth's atmosphere as hydrogen gas, okay, in its biatomic molecular form. It's wrong, I written bimolecular form, but it is available as diatomic molecular form of H2. Okay. And it is very, very common in the universe. Okay. Much less common on Earth, but it is available as water in a major form across the Earth. And it has utility in many applications. We will see what are these applications. The important thing to note here is that hydrogen has a very high converted into some other form, so it has a very high calorific value in that sense, but it has a very low volumetric energy density, because it is a very low density gas. Okay. And if you want to increase its volumetric energy density, then you will have to increase the density also, meaning you will have to compress it to a very high pressure in order for the density to increase. It is an excellent reducing agent. This is again something that is of importance, or it can be used in applications where the property of hydrogen to act as a reducing agent is important, like in steel making. We'll come to that also. But it is also highly inflammable, very difficult to store. Highly inflammable, meaning that it has a very wide flammability regime. So even if there is about 3% of air with hydrogen, then it can form a flammable mixture, and so that introduces challenges in terms of the storage of hydrogen, because any small leak can also cause or can create a flammable mixture, and if there is some kind of an ignition source, you could have an explosion. But it also is useful in the sense that you can have a very you can design a practical combustion device around this aspect of low, or wide flammability regime. Okay. So if you look at what problems we face, I'm sorry the graphic is not very clear here. This is the split of greenhouse gas emissions based on the sector. If you look at 25% of the greenhouse gas emissions overall, that is from industries. This is energy use in industries. This also includes any kind of electricity generation, so power plants and other industrial units. They contribute to about 25%. Then there is other applications in chemicals and ceramic industries and so on. And energy use in buildings is about 18%. Then you have unallocated and various other sources. So even agriculture has about 1.9% and so on. Now, when you come to the hydrogen, so this is a problem because you have all these greenhouse gas emissions, mainly carbon dioxide, which is the most highest, or rather the highest potential for global warming, and those are all termed as greenhouse gases. And in that sense, CO2 is quite undesirable product of any of these industries or various applications. Now, if you want to mitigate that, you would like to move towards hydrogen as a fuel, because when you use hydrogen in in a fuel cell or even in a combustion device, you only produce water, or either in the vapor form or in the liquid form, which does not contribute to global warming or to the greenhouse gas emissions. But this is not completely true, because water vapor has greenhouse or global warming potential fuel. The energy demand, okay, is increasing, and you can see that it is going to a very high value as we approach 2050. Okay? And the equivalent hydrogen requirement, if you are meeting the energy demand through hydrogen, would be about 7.5 gigaton. Okay? And this is the annual requirement. So there is a huge potential, but obviously you will have to match it with the kind of hydrogen production infrastructure which can accommodate this kind of a requirement, about 7.5 gigaton, which is a huge requirement. Okay, it's not so easy to produce 7.5 gigaton, because we are still looking at a few or 100 tons of hydrogen being produced in a year. Okay, and that is the target for the hydrogen valleys that are being established by the Department of Science and Technology across various locations in India. And this is only being done on a pilot basis. Okay? So imagine 100 ton as opposed to the gigaton of potential that is available, okay, or that is existing. So you can, or you should be producing it in gigaton capacity, but you're only looking at producing it at the a few hundred tons per year. Right. So, and the larger picture is that you are trying to move towards a carbon neutral economy, meaning that if you get rid of all hydrocarbon based fuels, which will produce both carbon dioxide and water as products of the process, the combustion process specifically, then if you want to completely remove the carbon dioxide from this process, then you will have to remove the carbon also in the fuel. Okay? And that is not possible with traditional or conventional fossil fuels, because they contain carbon. Okay? And when you oxidize these fuels, okay, to produce energy, you are essentially you're oxidizing both the carbon and the hydrogen in the hydrocarbon fuel, but you only want to oxidize the hydrogen and not the carbon. So essentially preferential oxidation of hydrogen is, of course it is possible because hydrogen is much more reactive, but completely avoiding the oxidation of carbon is not possible. So you are going to produce carbon dioxide, and to avoid that you will have to get rid of carbon from the fuel also. Okay? And the solution to that is hydrogen or hydrogen carriers. Okay? That can take you towards what is called as carbon neutral life cycle, meaning that if you don't have any carbon based fuels, you are not contributing to the carbon dioxide emission to the atmosphere. Okay? It is also possible to have a carbon neutral life cycle if you use biofuels which do contain carbon, okay, because they are made from bio sources, namely biomass. You can have biological processes, anaerobic digestion, which will produce biogas and so on, or you can produce bioethanol and so on. Or it could be gasification of biomass, which will produce carbon monoxide and hydrogen. Again, that is a fuel which is called as producer gas. So all of these have sources in plant matter, plant and animal waste, and they contain carbon. But what can be ensured is that you plant more trees, or you have a equivalent fixing of the carbon dioxide from the atmosphere by the plantations, which will ensure that in the complete life cycle, the amount of carbon dioxide emitted by the combustion process is again fixed by whatever trees you are planting. Okay, so that essentially means that the carbon emissions is equal to the carbon that is removed from the atmosphere by your trees. Okay, and it is possible only through the photosynthetic process. Other than that, there is no way of fixing the carbon from the atmosphere. Of course, you can always capture the carbon from the combustion sources or the emission sources, and then store it in the form of various okay. And if, especially for, let's say, mobility applications, which is again the focus of this FDP. If you want to store hydrogen and operate a vehicle, it could be a truck or even a small car, then you will need to store the hydrogen on board, and you do not have a lot of space on board. Okay? So you will store it in a cylinder. Let's say it is a 1 meter cube cylinder, and if you are only storing it at 1 kilogram per meter cube, then you are storing you can only store about 1 kilogram. Okay, and in fact it is not 1 kilogram per meter cube, it is much less than that. But if you compress it, okay, if you increase the pressure, the density also increases, which means, let's say it goes from 1 kilogram per meter cube to 2 or 3 kilogram per meter cube. In the same volume of 1 meter cube, you are now storing twice the amount of hydrogen. Okay, so which is what we try to address. Okay, so hydrogen production is one challenge, but it is a totally different issue when it comes to storage of hydrogen. Not just because of the very low density, it is also because of the fact that it can leak quite easily, and it can also cause, for instance, it can cause embrittlement of steel, so you cannot store it for very long durations. There can be leakage which can cause explosions. So these are all issues that we will face with hydrogen when you are trying to apply it to mobility applications specifically. So the density is, as you can see, 8.9 into 10 power minus 3 gram per centimeter cube. The density for liquid is 70.8. It's only about 10 times the density of gas. So it is not a huge improvement, but yes, you have an increase in the density, which is good. Okay. And the heating value, as you can see, is 142 megajoule per kilogram. When you compare this with the heating value or the calorific value of typical fossil fuel like petrol, it is about 3 times. Okay. The calorific value of diesel or petrol is about 42 megajoule per kilogram, and this is about 3 times that, a little more than 3 times that. If you compare, the energy density of gasoline is 46 megajoule per kilogram, and this is the difference. So 142 to 46, about 3 times, as I mentioned. Right. All of these are again not really important, although the ignition temperature is important. It is, we call hydrogen as a very flammable fuel. Okay. But the ignition temperature is about 585. So you need a source which has a temperature of around 585 for it to be ignited in for it to combust, essentially. Okay. But the flammability limit is quite wide, meaning if you have in a volume of air, only 4% of hydrogen is sufficient to ignite the mixture, and it can ignite up until about 75% by volume of fuel, okay, in air. Okay. So if you have 75-25 as the ratio of hydrogen to air, it can ignite, and even as low as 4% can ignite the mixture. So this creates an issue in terms of storage. And this shows the various pressures, what is the energy content per meter cube. So this is the volumetric energy density. It does increase, but the pressures that we are looking at are 200, 550, 700 and 800 bar, and correspondingly the energy density increases from 2.53 to 10.12 into 10 power 3 megajoule per meter cube. Right. This is something that will be discussed again in the afternoon session by Professor Sundarajan, but I'll just very briefly talk about the colors of hydrogen. Now, a lot of you are familiar with the terminology green hydrogen. Okay. That's what we are targeting, but there are other colors also to hydrogen. Green hydrogen is termed as the hydrogen that is obtained from the electrolysis of water. But this electrolysis must be carried out with you require electricity input.
Hydrogen from the gases that come out, and very often, some water vapor also may come. It may not. That's why we have the condenser and everything. The setup has, as you can see, some condenser, water trap, moisture trap, all those things to get rid of any water vapor. And then if you want to get only hydrogen, here we didn't worry about that, so we got the gas out and measured how much hydrogen is there in it. But if you want to separate hydrogen from carbon dioxide, you must use some separator to do that. So for example, you can have a membrane can be used whose pore size has to be appropriately selected. There are many membranes, zeolite, so many of them are there. Krishna mentioned about that. So by which you can separate the hydrogen from the carbon dioxide or any other product which may be there. Now we go to water splitting and this chlor-alkali process. Here, in fact, we have not worked on chlor-alkali process, but we have seen this being done. For example, in ISRO, they have liquid hydrogen at cryogenic conditions, very low temperature, 20 Kelvin at high pressures and so on. Where do they get the hydrogen from? They basically do it by splitting water. So basically, they add sodium chloride, and sodium chloride in liquid form will come. And then when you do the electrolysis of that, chlorine will come out, and sodium will pass through a membrane. All right. So membrane must have porosity to allow the passage of sodium. And on the other side of the membrane will be water. Sodium will react with water and produce sodium hydroxide, and water comes in into this part of the cell. and where when sodium reacts with water, it becomes sodium hydroxide, but hydrogen is not. So this is basically the chlor-alkali process. It has many good products. Sodium hydroxide is one product that they can produce. Chlorine is another product they can produce. Hydrogen is another product they can produce. In fact, we did go to industry in Andhra, in Rajmandri. They have Andhra Sugars, right? So they do make liquid hydrogen for ISRO, huge amounts. But of course, a lot of electricity is used in the process, and the water they use all extremely pure water. So it is possible to split. You are splitting water all right, but they are also producing sodium hydroxide and chlorine. So that, in fact, that is their main product. The Andhra Sugars, they are producing caustic soda and chlorine, and as a byproduct they are getting hydrogen, and the hydrogen then has to be cooled and then taken to cryogenic condition, etc. So that is being done. We went through the plant. It's really very, very interesting to see that it is possible to. So, I mean, if you look at the reaction as a whole, so chlorine and electron will go in the external circuit, and then water will be split as hydrogen and hydroxyl. Hydroxyl ion will react with the sodium to produce sodium hydroxide. So on either side of on one side of the cell, you may have splitting of the sodium chloride. On the other side, the sodium that passes through the membrane will basically split water to produce hydrogen. So again, an electrochemical way of producing hydrogen. And to enhance the properties of these electrodes, often you can coat these electrodes. The surface of the electrode can be coated also. We will discuss about that later. And I was mentioning about the two-step thermochemical water splitting. If you have a metal oxide, the metal oxide, when it is reduced, it produces basically it produces some oxygen vacancies. So oxygen vacancies, depending on what is that metal oxide, the temperatures can be 1200, in fact, we found even from 900 onwards good activity. So oxygen vacancies are produced. And then this reduced oxide is a very active component. On that, if you pass steam, from steam it will pull the oxygen, once again go back to the original state, and hydrogen gets produced. So there are, as I mentioned, there are many such metal oxide catalysts like ceria or ferrous compounds, etc. So at different temperatures, it is possible. So a lot of heat is available from some source. It is possible to therefore use these metal oxides, which undergo. It's almost like a reversible kind of reaction. Metal oxide gets reduced, and once again it gets oxidized when steam is passed, goes back to its original state. And in the process, some oxygen is evolved at some temperature. Slightly at a lower temperature, hydrogen is produced. And so this process can be repeated back and forth. So you can also have, when ceria is used, ceria, as I mentioned, there could be, let us say, centering kind of processes can happen. You can use, let us say, zirconium. Zirconium and ceria are good friends in their size and so on. It is possible to really have a kind of base, zirconia on which ceria is really mixed at them. So it is possible to get probably in the form of either powder or in the form of some coating or even honeycomb. So various kinds of structures can be evolved, and then hydrogen production as a function of temperature. You can produce thermochemically, you can split water and produce hydrogen. Obviously, when you go to higher temperature, this reduction reaction becomes favorable, very favorable. So more hydrogen can be produced. As far as the other step is concerned, this doesn't require high temperature, but splitting the higher oxide, that will require some heat input and high temperature as well. I also mentioned about iron being a possible candidate. Oxides of iron against ferrous oxide, ferric oxide, or magnetite. These are all different oxides of oxygen. It is possible again to go between ferric and ferrous in a very similar kind of two-cycle process. What is the advantage of two-cycle process? One advantage is they happen at different temperatures. So which means this happens at some condition, this happens at another condition. Hydrogen and oxygen don't come simultaneously. So you first get the oxygen out, take it and store it somewhere. And what is the active reduced oxide on which you pass steam? Only hydrogen will come. So separately, hydrogen and oxygen can be obtained from here. So then, I must give the reason also. In one of our, let's say if you split water, how much hydrogen should come, how much oxygen should come, we know. But it so happened we are getting more hydrogen than what we expected. Where did the additional hydrogen come from? We didn't understand it. Then later on we found that the metal pipe in which hydrogen was passing through, it was reacting with the metal. The pipe was getting oxidized, metal was getting oxidized. So in the process, metal pulled oxygen from water vapor and produced hydrogen. So we got more hydrogen than what was expected. Oh, that means it's not even metal oxide, even metal itself will react also at higher temperature. Then we said, oh, okay, then why not try that process? So we collected a lot of scrap materials in any workshop or anywhere. Many metal products are there. Finally, they are thrown into the garbage. Alright. So if you can collect that scrap and put it in the furnace, can be produced by, let's say, passing steam over that. Is it possible to produce? We are able to produce hydrogen that way also. For example, iron scrap from workshop we collected and pass steam over that. So it can become, this is magnetite, and then hydrogen is produced. Or again, iron plus water vapor can produce, this is ferrous oxide and then hydrogen. This is ferric oxide and hydrogen. So it is possible to produce, let us say, iron and water vapor. We can produce hydrogen out of that. The temperatures at which this will take place, depending upon the process, the temperature can be different. We primarily produced hydrogen through the first one. This was producing good amount of hydrogen actually from metal scrap and iron filings which we collected from workshop, etc. And temperature in the range of around 1000 degrees it was produced. There are also processes that people talk about in terms of what is called as hydrothermal catalysis. In the presence of some catalyst, let us say, in a liquid medium, it is possible to produce also. This has been reported in literature, but what we have done is completely all are gases only. Only iron is the form of a powder, or rather scrap, iron filings, on which you pass steam and you can produce hydrogen from it. This also, in fact, was a paper that has been published in Journal of Hydrogen Energy. Hari Krishna has just submitted his thesis. And what we found is that when you pass steam over, let's say, iron filings, so somewhere around 1000 degrees, there is a sharp, this is actually what is called as a TGA. TGA stands for thermogravimetric analysis. So basically, it is a kind of very fine balance. A balance in which you keep the sample, and the sample is, in fact, it's in a furnace. The furnace can be heated to whatever range of temperatures, so you can increase the temperature. So initially you find that nothing much, if anything, in fact, from the sample, because it is scrap, maybe it had some moisture, etc. So it's little bit of moisture and maybe other some water gas, it went down. Then somewhere around 900 degrees, it started picking up oxygen from steam. So steam is being passed over iron, so it picks up oxygen from that and then reaches steady. So by looking at the increase in weight, we were able to find that it will be essentially, mainly it is magnetite is getting produced. And so, so then we studied this process in detail by varying the particle size, by varying the temperature, etc. So we are getting somewhere in the range of about half a liter per gram of scrap. Alright, half a liter of hydrogen per 1 gram of scrap. And of course this volume that we talk about is all at NTP, normal temperature pressure. So good amount of hydrogen we are able to get from this scrap material. So it's almost like waste to wealth. scrap is thrown out, you might use it for with the steam to produce hydrogen. So orientation nothing was seen, but then as you keep on applying this just again and again with time, the grains are getting oriented slowly and the performance becomes somewhat better. And here this flame heat treatment, after that it became a bi-directional catalyst that both ACR and OER were possible. So you may say that because platinum is not used, only nickel and ceria are used, so it's an inexpensive flame treatment based approach was used to, basically this heat treatment was doing annealing of the electrode deposit coating, basically of stainless steel substrate, and it boosts the activity towards HA. Earlier, before heat treatment, the hydrogen evaluation reaction was not happening. But after the heat treatment, the changes that happened in the microstructure really helped in both the oxygen as well as the hydrogen evaluation. And so, using this cyclic voltammetry technique, we are able to understand the rate at which it is happening, both in the forward as well as reverse direction. And the stability test showed that even after one full day, still it had good activity. There was no change. Normally, what happens is that if you cyclically, if you keep on using any sample, even mechanically, you are loading, deloading. After some use, it will fatigue. Its sync goes on. Particularly with catalyst, very often what will happen is after some 1 or 2 or few hours of operation, its activity goes on. But that was not happening here. We found that it was still quite active even after, let's say, lakhs of cycles done for a long time. So, as such, it turned out to be a good test for stable catalyst which has bidirectional catalytic activity. Yeah, and in fact, this test was done cyclically. So you will see that in the positive side, you keep increasing the voltage, then come to the negative side, decrease it, once again increase it, once again decrease it. Like this for hours, it goes on, and you see that it was performing very well for both the OER as well as HCR. That by looking at the current value itself, you know how much hydrogen has evolved. That can be calibrated. So really, you can get the amount of hydrogen has evolved by looking at the current value for. Should we break or can I continue?
Break is a free.
Break or?
It is 41 minutes.
40 more. You can finish the whole thing.
Yeah.
Okay, good. I'll do. No problem. So then the last technique that I'm going to talk about is photocatalytic water splitting. We talked about chemical methods of producing hydrogen, either from water and maybe some metal scrap, or from ethanol using some catalyst, or to split ethanol, bioethanol, and then get hydrogen out of that. And in the electrocatalytic method of splitting water with coating on the electrode, how to enhance the oxygen evolution reaction, how to enhance the hydrogen evolution reaction, etc. But in all of these are all somewhat, you can say, indirect methods of splitting, in the sense that you are providing energy in the form of electricity, and that electricity may come from somewhere. Now, the photocatalytic method is a direct method, in the sense that whatever energy you are getting from sun, directly use it on the electrode, and in fact the material that you use must have photoactivity. Basically, titanium dioxide is a good material for that. It can absorb the photon, energy of the photon, and then that photon convert that into electrical form, and then initiate these oxidation reduction reactions to really split water. So basically, it involves, let us say, so this is H nu, is basically the light that falls on it. And there are several things that are happening. here we have to look at this oxidation, reduction, etc. in a very general sense. Not necessarily oxygen may be there, may not be there. The reactions that happen, several chemical, I have not gone to that, I'm talking about the phenomena that are happening. That, as far as the electrode part is concerned, the semiconductor materials are being used there. And semiconductor materials are, let's say, their charge carriers are E minus and electron and electron holes are there. And that is what is happening on the surface of the electrode. Photon comes and hits, then photon is able to emit E minus and electron hole also. Electron holes are being produced. There is a possibility that they may recombine. Temporarily, photon hit on the surface, electron hole pair are produced, and the pair recombine and gone. So somehow we must be able to separate this electron and electron hole and provide good conductivity for them to get conducted towards, see, a positive charge eventually should go to the, let us say, cathode side, and this one also. So we must help the transport also. So those are phenomena that need to be done. Recombination needs to be avoided. If it recombines, the effect of this photon is gone. Basically, when they combine back, some heat will get produced and heat will be lost. So we must therefore also avoid this recombination and allow for transport of electron holes, etc. So those things are also to be something to be kept in mind. So if you look at it in a slightly detailed manner, so what has been done is that, so you have, let us say, the TI plate, all right, plate is there, on which these are basically titanium dioxide nanotubes. Titanium dioxide nanotubes have been grown on the anode side. So this is being called as TNT. So TNT stands for titanium nanotube material. So the growth of titanium nanotube, how is it grown? For that, all right, so while the growth of this, there's a titanium metal substrate is there, and we have titanium fluoride is there around it, all right, with which electrolytically it is possible to deposit, all right, some, you can grow nanotubes of titanium dioxide is possible. And so this is basically growth of nanotubes on the electrodes. Because the nanotubes, nanotubes are basically titanium dioxide only, but now this has very large surface area. So there is large, because nanotube means, the diameter is of the order of, let's say, nanometer, and for the volume that it has, but it has a very large surface area. So once you have created the nanotubes of large surface area, that really helps in the process of converting the photon energy into electricity. So sometimes you don't have to have a purely titanium thing. You can also, this is actually titanium, aluminum, vanadium alloy, TAV. So this is the substrate, titanium, aluminum, vanadium alloy. You clean it, polish it, etc., then anodize it. After that, it is possible to grow nanotubes on this. And then, so once the nanotubes are grown, this becomes the electrode. So that is used for PEC catalytic. PEC stands for photo-electro, we call it photo-electro-catalytic or photo-electro, so basically photoelectrochemical, because the chemical reactions are happening, and then in the process this nanotubes which are having very large surface area, that really helps. And what we found is that, okay, this is just to grow the nanotubes, but you don't grow the nanotubes just like that. The atmosphere around it, we have tried 3 different atmospheres. Let's say around this, let's say you have ammonia or nitrogen or air. Now what is the role of this nitrogen, ammonia, air, etc.? What is happening is, while this growth process is taking place, when you have nitrogen, some nitrogen gets incorporated on the surface. And that, in fact, it seems to reduce the band gap, so that the absorption of photon is improved. It also seems to help in keeping the atmosphere, either ammonia or nitrogen or air. We found that annealing in nitrogen gave the best results with respect to the performance of this photoelectrocatalytic procedure. This ammonia was in between and air was the least in terms of performance of the photocatalytic activity. So how to grow the nanotubes? The process begins with the formation of compact titanium dioxide hydroxide barrier layer, on which the electrolyte has titanium fluoride, and then so this titanium fluoride, what it penetrates and then creates localized dissolution, etc., nanopores, and then guided by the electric field, these pores evolve into nanotubes through material redistribution. That's how the nanotubes are grown on this. And so the once the nanotubes are, you can control by let's say controlling the concentration of titanium fluoride, by controlling the electric field, etc. It is possible to control the growth of nanotubes, and anodization voltage is also important. So these are parameters that influence the growth of these nanotubes. In fact, if you provide higher voltage, then poor growth, but it disrupts the uniformity. So one has to really play with them and come with optimal kind of operating parameters to have very uniform growth of nanotubes. And these TNTs exhibit double wall structure, some variation in the let's say within the object. The inner walls and outer walls, they have slightly different chemistry, and so in fact I would say this is still an evolving area. So I won't be able to explain to you exactly what it is, but we find that the inner and outer areas are not exactly same. There is a difference in the. So after they are annealed in the three atmospheres, ammonia, air, and nitrogen. So this is the kind of ACM image you can see. So it shows that these are nanotubes. So you can see the inner wall, outer wall, etc. of the tubes. And the structure is somewhat different depending upon what is the annealing atmosphere being used, of course. But still, overall the structure looks reasonably good, but only problem is that. But okay, I want to highlight something. Among the three, if I ask you, which has the best structure? The second one are fairly uniform sized nanotubes, no defects. Here you see some defect is here, some defect here. So it's not exactly uniform size. So with ammonia, we find that ammonia also not somewhere here and there you see defects. If you ask a question with respect to this photocatalytic activity, is something with defect better catalyst, or the one which has very regular structure is not good for, because once it is regular, stable, etc., it doesn't have a good activity. Only surfaces with defect, they are active, because the defect is bothering. It creates some kind of let's say unequal energy. So a surface which has more defects is somewhat helpful. So what we find is that nitrogen annealed surface, where you see this kind of this is not there is no nanotube here, there is no nanotube here, there is no, this has more defects. The one which has more defects is performing better. That is what we find. Anyway, so we have grown that this is 3 electrode setup. So we have working electrode, counter electrode, and there is a reference electrode. And this is about the let's say the electrochemical cell. But in between we have something. So this is, let us say, to produce the light. We didn't do it in the sun itself, but a xenon lamp, arc lamp is a reasonably good simulator for solar energy. So this is a xenon arc lamp. Now we wanted to conduct experiments where the shutter experiment. And basically you don't want the light to go continuously, you keep on intercepting. If you intercept and then do measurements, you will get data about what happens when there is light, what happens when there is no light. Okay? So because please remember that in the case of an electrochemical cell, you are always applying voltage. All right? You are